Hello class, welcome back. Today we will start a new chapter. So this is chapter 7. This is the chapter 7 handout in your Canvas repository. So you can find it on Canvas, and you should probably crack it open for this class. So before we go on to fill in our PowerPoint worksheets, I just wanted to outline the main motivation behind chapter 7. Why is the necessity for students at this stage to know about dimension analysis and modeling? The straightforward answer is it gives you a dip into the world of modeling, engineering designs. So how do you connect what experiments you are doing in your laboratory? How do you connect it to real world engineering problems? So that is what is the main usefulness of this chapter. So in real world and in engineering problems, most of the time what you see is to save time and money. Tests are being done on geometrically scaled models rather than on full-scale prototype, taking into account the economics and the cost expenditures involved. So first we select a geometrically scaled model. Next, the engineer is expected to scale the results based on the experiments what he or she conducts on the small scale model. Okay, and then scaling is done. The procedure for scaling is done using the concept of dimensional analysis, and what you will be learning in this chapter. And so the purposes of dimensional analysis are: first, generate non-dimensional parameters to help in the design of experiments. Essentially, what we do is whatever results we get in our bench scale or laboratory scale models, we have to normalize our results. First, obtain scaling laws so that the prototype performance can be predicted from model performance. And most importantly, we have to predict trends in the relationship between the different parameters in the scaled expression. So that is the basic, the fundamental objective and usefulness of this chapter. With this, let's move on to our worksheets. So actually see the benefits of dimensional analysis before applying the tools to simple models. Okay, so let's get started. This is from your first chapter, dimensions and units. What's the difference? So dimension is a measure of a physical quantity. Right? For instance, in this case, length. Unit is a way to assign a value or a number to that dimension. So what are the 7 primary dimensions or fundamental dimensions, what we call it? First is, as we have seen, mass, m, length, l, time, t, temperature T, this is capital T, electrical current I, amount of light C or candela, amount of matter N, or like you have moles, like so this is the Avogadro's constant, or like you have moles. So in PChem you have seen that, as well as in your freshman chemical engineering class. So then you have the non-primary dimensions formed from primary dimensions. So example is surface tension. Surface tension has dimensions of force per unit length. In terms of primary dimensions, what will it be? So force is M T square, okay. So this is how we use the 7 primary dimensions to deduce non-primary dimensions. Okay. So next is the law of dimensional homogeneity. It's basically what we have been seeing in most of our equations, analytical equations we have seen in this class. Your left hand side and your right hand side must have the same units, and what it means that pictorially you can only add apples and apples and not apples and oranges. Okay, so best example we have seen is the Bernoulli's equation for incompressible irrotational flow. This is the energy equation, and so does each term have the same dimensions, right? That's what we will see. So let's check the pressure term. Again, this is a must thing. You need to have the dimensions all to be same in order for equation to be valid. T square L. Okay. What about the second term, half rho v square, the kinetic energy term? Half does not, so half is a constant, so density is mass volume times velocity is distance over time, so square. Okay, so what about rho gz? Rho is again m over L cube. G is distance over time square, and G is just distance, which is m. So here in this case we have checked the dimensions, all three of them are same. So what are the dimensions of C? Again, remember that for this equation to be valid, your left hand side dimension should be equal to the right hand side dimension. So C is m Okay. All right. Now we come to the first concept of non-dimensionalization. So just to give you some perspective, this particular equation, as you scale a system, your variables will also change. Pressure term will change, density term will change, velocity will change, right? So pressure, velocity, and of course z, height, will also change. These are the prime terms which will change. So if you do a set of experiments using the variables of pressure, velocity, and z height over for a bench scale or a lab scale apparatus, and you find a particular answer, how do you convince the industrial side of people, or large scale system engineer, that your results are applicable to their systems? So what we do to get around this problem is we non-dimensionalize the different terms in this equation and make it such that all the variables, the equation is basically normalized such that each term here has an order of each term is of order unity, meaning that the equation is valid even for any scale system. So this is the first step we have to adopt. And how do we go about it? Okay, so again, non-dimensional equation, one whose terms are dimensionless. And how do we do that? We create by dividing the variables or constants of the same dimensions. So equation, basically each of the terms in the equation, like in this equation we saw, these terms will be of order, each term will be of order unity, and then we said the equation is normalized. Each term is of order unity, that is 1. Okay, so let's take the simple equation of motion which you have seen in your freshman physics or high school physics. Acceleration due to gravity, and this is the differential equation, and we integrate to find how does distance or height change with time, right? So here, what are the dimensional variables? Z, t. So dimensional variables are z and t. And what are the non-dimensional variables here? Really, there are non-dimensional variables are quantities that change but have no dimensions. Example, angles. We do not have any here. Okay. Now you might be wondering, what about Z naught, W naught, and G? So these are dimensional constants. G, Z naught, W naught. And then you have pure constants such as half, pi is a constant, E exponent. So you will find a set of equations to be a mixture of these different ingredients. Okay, so to non-dimensionalize, first we scale the parameters. So what we do is we select first the scaling parameters based on the primary dimensions in the original analytical equation. So we'll solve this here, but what I want to say here is first step is we find out the primary dimensions. In order to select the scaling parameters, first find out the primary dimensions. Fluids, usually we need greater than or equal to 3 because problems have 3 primary dimensions as such. Length, velocity, pressure. In the above problem, the above example, you see that our primary dimensions are length and time. So here basically we have 2 primary dimensions. Right? Now once you choose the primary dimensions, then you use from the dimensional constants, which is Z0 and W0. You could also choose Z0 G or W0 and G to basically form your scaling parameters. Okay, so let's see how we go about applying this non-dimensionalization to this problem. Okay, so first step, as I said, list all the primary dimensions. So what are the primary dimensions we have in this equation? Z, length, T is time, Z0, which is a dimensional constant, length, W0, is velocity, and G is acceleration. Okay, so first we have listed out the primary dimensions of all the parameters. Now we divide the dimensional variables by the scaling factors to obtain the non-dimensional variables. So the scaling factors, again, we base the scaling factors off of the primary dimensions. So primary dimensions here are Z and T. Now we non-dimensionalize them. That is why we haven't put an asterisk here, because they will not have a dimension. So Z we divided by a dimensional constant, Z0, T, W0 T divided by Z0. So you see here how we non-dimensionalized Z and T, the two primary variables, using the dimensional constants, combination of them. Okay, using a combination of dimensional constants and so dimensional variables. So now we substitute these non-dimensional variables into the original equation. So our original equation is this. So we use Z becomes Z star Z naught divided by D star Z naught square. Equal to this D square Z star dt squared is equal to minus G. Right? So this is that equation, and what we find, we can also write this as G squared minus 1, right? So this equation. So this particular term is what we call it as the fruit number. Just like the Reynolds number you saw, this is the fruit number, which is essentially the form is this is the form. What does it say? It gives you the ratio of inertial force gravitational force. So this number tells you the tug of war going on between gravitational force, between inertial force and gravitational force. And so essentially you can now write your equation of motion under free falling gravity using your Fruit's number. When we integrate it, Z star one plus D star minus so here we have seen a very different way of essentially solving this differential equation. So what we have done is we have first non-dimensionalized the variables, the fundamental variables in this equation, Z and T, and then we cast this analytical equation, this differential equation, to tease out the Fruit number and then express the equation in terms of a non-dimensional number, which is the Fruit number, and then we solve it. So this what it does is it increases insight into relationships between key parameters. So that is one of the first advantages of non-dimensionalization. It gives you a relationship-based insight into how what are the driving mechanism of an equation, what are the driving forces in a particular equation. So for example, in this particular case, this gives insight into relationships between key parameters here. The particular example is if doubling of W naught has the same effect as decreasing height or Z naught by 4 times. Right? This is what this gives you. The other thing, what is the advantage of non-dimensionalization? We started off, it basically reduces the number of parameters in a problem. Example, we started with two-dimensional variables Z and T and three-dimensional constants G naught, W naught, Z naught. Our final expression form has two variables and one constant. So really this is more of a semi-quantitative way for engineers to solve complicated problems, right? So this is, I should say, one way to solve complicated problems, because we can't always have analytical solutions handy. And even in my own research, if you look at my publications, I use a lot of these scaling based analysis, because in chaos theory, in chaotic environments, chaotic situations, you cannot always solve the governing dynamics equations. So what we do is we essentially non-dimensionalize the variables and find scaling behaviors. So that is a very standard way, in condensed matter physics as well. And this is what the engineers used to. So this is a pictorial way. For in the previous example, you could have all different charts for the three-dimensional constants and two-dimensional variables, or you can simply have one chart as a function of t star and z star, two variables, and the fruit number. So this really decreases the reduces the parameter space and makes use of handy charts. So what you saw in chapter 8, for instance, the Moody chart using Reynolds number and friction factor is another example. Okay, so these things you need to really practice problems, how to do it. Again, the rule of thumb is you first start off with primary dimensions and then use the combination of dimensional constants to form the scale factors, and then plug and play into the governing equations to come up with expressions which include non-dimensional numbers like the fruit number, or it could be even Reynolds number, or it could be a whole different gamut of numbers you will see. Okay, so again, dimension analysis, the practical usefulness for the scope of this class is in engineering, equations often unknown or too difficult to solve, so we non-dimensionalize. Non-dimensionalization is difficult. Instead, what we do is we run scale down experiments on model, and then we scale it up based on relationships such as what we saw here. The key parameters like doubling of W0 has an effect of decreasing Z0 by 4x. So we make such inferences and we use it for scaling up of systems. So while scaling up, there are three different principles we should follow. Really three necessary conditions for complete similarity between model and prototype. So first is the geometric similarity between your prototype and the system which you want to scale. By geometric similarity, you mean that you have the same shape, you are scaling by a constant. So this is when you are scaling up for a geometrically similar system, you call it length scale equivalence. So your prototype and your model, the only way they are varying is based on the length scale, the geometric length scale. Then you have kinematic similarity. Kinematic similarity is basically the parameters, like for instance in a pipe system, right? You have velocity as a parameter. So velocity in model flow proportional to velocity at same point in prototype, such that all you do is just find out the proportionality constant and apply it to the prototype. Here thing to note is that the direction should be the same. The only thing which needs to be scaled is the magnitude. This is also sometimes known as the temporal scaling equivalence or time scale equivalence. The third type is the dynamic similarity. Here, the system are driven by the same forces. So the model and the prototype are basically, the forces are the same, only difference is the scaling factor. And the thing to note here is that your scaling factors don't have to be the same for all three types. It can be greater than, less than or greater than equal to 1. The thing to note here is that for geometric similarity, should be considered as a prerequisite for kinematic similarity. However, kinematic similarity is necessary, but just having kinematic similarity might be insufficient for applying dynamic similarity. So for kinematic similarity, this is a must. For dynamic similarity, this kinematic similarity is necessary, but just by having kinematic similarity, you cannot absolutely say that a model and a prototype are dynamically similar. There are other conditions which need to be satisfied. Okay, so now how do you put this knowledge into practice? Meaning, how do you mathematically solve or apply the principles of similarity between a model and a prototype? So the first step is, for both a model and a prototype, list down the non-dimensional parameters. And the non-dimensional parameters, next you assign them as pi's. Okay, so that is why this chapter is known as life of pi's. Basically, the non-dimensional parameters you list down as pi, and then you figure out the dependent parameter, the dependent pi, which is essentially a function of the independent non-dimensional parameters. So do this step for both the model and the prototype. Next is, for complete similarity between the model and the prototype, each independent pi, that is on the right hand side here, in the model should be equal to the corresponding independent pi in the prototype. That is pi 2 model, pi 2 prototype, pi 3 model, pi 3 prototype, etc. Under these conditions, your pi 1, the dependent pi, is guaranteed to match between the model and prototype because your right hand sides are scaled or matched. So we will now use this concept or idea to perform dimensional analysis on unknown engineering situations or design situations. Okay, so first let's look at a multiple choice question. Surface roughness, what we saw E in chapter 8, or small protuberances must be equated between model and prototype in order to achieve what kind of similarity? Again, remember the three types of similarity. Geometric similarity is same shape, or it's just scaled by a constant length scale equivalence. So here we are talking about physical similarity, so it has to be geometric similarity. Okay. If the velocity ratio and the acceleration ratio for model and prototype are constant throughout the flow, then the systems have, so the velocity ratio and the acceleration ratio. Okay, so we are talking about, going back, velocity and acceleration. Essentially you're looking at the temporal scale here, like at the same point in time you're looking at the parameters of velocity and acceleration. So they must have kinematic similarity. So if velocity and acceleration ratios are constant, streamline patterns will be the same. Okay. Next is a design MCQ. An engineer designed a model airplane using a 1/20 or 1/20th length scale model of the wing. Okay, the area of the scale model of the wing is A, the same as that of the actual wing, B, 1/20th that of the actual wing, C, 1/400th of the actual wing, and D, 20 times that of the actual wing. So what do we have? 1/20 is the length scale. So your area scale will be length square. So which is how the scaling for area should go, that is C. Okay. All right. Next, a 1/10 scale model of an airplane is tested in a wind tunnel. The Reynolds number of the model is the same as that of the full-scale airplane. The question is, the velocity in the wind tunnel is then dash that of the full-scale airplane. So remember again, what was the Reynolds number? It basically describes if the flow is laminar or turbulent, given by rho v d mu, right? So in this particular case, if the Reynolds number between the model and the prototype, in this case the model and the airplane, has to be the same, and you have the diameter is equal to 1/10, right? So the diameter here is decreased by 1/10. So in order to keep the Reynolds number same between the model and the prototype, what should be the velocity? V has to compensate, right? It has to be 10 times to compensate. So C. Okay. Next is a problem. It's from your textbook, right? So we want to predict aerodynamic drag of a car at 50 miles per hour and temperature 25 degrees Celsius. So just like most design problems, engineers first built a 1/5 scale model of a car to test in the wind tunnel how it would perform. It's winter and the tunnel is unheated, that is, the actual temperature is around 5 degrees Celsius. Density of air at different temperatures are provided, viscosity is provided, right? And for incompressible flow, the aerodynamic drag has two non-dimensional parameters, the dependent and the independent parameters, where pi1 is this drag force, pi2 is your Reynolds number, independent, right? Dimensionless. Now, how fast should the engineers run the wind tunnel to achieve similarity between the model and the prototype? So, how fast it's asking is to the velocity Vm, right? So this is what is being asked. Okay, so how do we tackle this? First, we see the independent and the dependent parameters, as we saw how to tackle such problems of similarity. So since we have only one independent pi, which is the Reynolds number, really your similarity is achieved so similarity is achieved again. I'm going back to the slides. Similarity is achieved if you match your independent pi's between the model and the prototype. So since there is only one here, one independent pi. Similarity is achieved if pi 2 m is same as pi 2 prototype. Okay, so what is pi 2 model? Is the Reynolds number of the model, which is rho m Vm Lm mu m. This should be equal to pi 2 prototype, which is equal to Reynolds number of prototype equal to rho p Vp Lp divided by mu p. Right? Okay, so then what do you get? Vm is equal to Vp. You're just equating pi 2m and pi 2 prototype. Rho p rho m mu p, which is equal to velocity is 50 miles per hour, Lp over Lm is 5, rho p over rho m 1.184 divided by 1.269 mu m at 754. 1.84. So your Vm is 221 miles per hour. So you see here, for the similarity types of problems, all we did was equate the Reynolds number, which was an independent non-dimensional parameter pi. Okay, so follow up to the previous problem. The wind tunnel is run so as to achieve similarity. The aerodynamic drag force on the model is measured to be 21.2 pound force. What would be the drag force on the prototype at 50 miles per hour and 25 degrees Celsius? Okay. So here, what do? We are asked about the drag force. The drag force is your pi's. Pi 1, the dependent pi. So this is basically asking what is pi 1 model, pi 1 prototype. Now that we have matched the similarities. Okay. So rho p, just rho p, vp, lp square, lp square. FDP is FD model times rho P rho divided by rho M VP square. So 1.184.269 So the thing to note here, whenever you're doing when you are equating pies, is that mixed units do not really matter because you're taking ratios. Just know what to equate. That is the most important thing actually. Don't matter so much. So TP 25.3 pound force. So the other thing to notice is that it doesn't matter what fluid is actually used in the tunnel. So long the pies match, you are good to go. We could have also tested the same model in water instead. So why might want to do that? Water, because you would require much lower speed. Okay, so this I would call it a good stopping point. Next class we will finish this chapter. So this chapter is, as we have seen, it's all about finding out the non-dimensionalized form of an analytical expression. First is that the technique we saw. Basically target your primary dimensions, and from there you go about non-dimensionalizing an equation. So that is what we saw here, right? This slide is important, and how we solve the equation of motion. Once we do that, we will see that certain intuitive terms fall out, and our forefathers, the moment they saw this, the first one to see it and catch it, they have named it after them. In this particular case, the Froude number was one, Reynolds number being the other one you saw. And then the non-dimensionalized parameters or the variables. Next, what you do is you cast them as pies, non-dimensionalized parameters, pies. And basically you cast your dependent pies, independent pies. And why do we do so? Because we want to find similarities, either geometric, kinematic, or dynamic, to basically scale a model and a prototype. Okay, this is how most of the experiments are done in the laboratory. You start to play around with a model, and then you want to basically scale it up. And how do you scale it up? Again, you have to make sure that your independent pies, so long they are equated between the model and the prototype, you are good to go. And that is what we saw in this particular example, where we equated the different, there was only one independent by the Reynolds number, and we equated them, and we made the model and the prototype, basically found out what velocity needs to be there, such that the the testing done on one suffices the other. Then we also equated the dependent pi to find out what drag force is necessary. Okay, so this is pretty much it. It's actually a pretty easy chapter. All you need to do is just understand the concepts and practice some problems. It's a pretty plug and play sort of a chapter, as you have seen in this quiz problems, where in this MCQ problems, where you see, okay, what should be the scaling factor for area? Well, it's a length square, so that's how the area is being scaled. And what do you need to do between a model and a full-scale airplane if the Reynolds number were to be the same? You basically see which parameter is being decreased in your model, and compensate for the other, such that the Reynolds number is conserved between the in this case the airplane and your model plane. So it's just, I would say, a very common sense sort of, you have to apply your common sense, know which pi's to equate, and it's pretty straightforward from there on. So hope you have wrapped around your head with whatever was taught today, and if there are any questions, feel free to send me an email, and I'll see you in the next class again. Thank you.